Hello, and we're back. And just like that, we're in chapter 8, if you can believe it. All right, so chapter 8 is going to be all about, well, we're going to start with confidence intervals as a general term, and we're going to begin with proportions. So we have quite a bit of learning targets today. This lesson will probably be broken up into, I'm thinking 2 days. So if you're trying to watch this for class, just try to figure out where you think is a good point to stop. So a lot of vocab, and it's the kind of vocab where we have to be really particular. So we're going to really watch our vocab during this, frankly, this whole class, but this chapter in particular. So our first piece of vocab, we have what's called a point estimator. It's a statistic that provides an estimate of the population parameter. So remember, a statistic is for our sample. Population has parameters. The value of that statistic from a sample is called a point estimate. So here we have an example, some sample data where identify the point estimator you would use to estimate the parameter in the following situations, blah, blah, blah. All right, quality control inspectors want to estimate the mean life, and they're using mu for the population parameter of AA batteries produced each hour at a factory. So of course they randomly sample, in this case 50 batteries during each hour of production, and then they drain them under conditions that mimic normal usage. Here are the lifetimes in hours of the batteries from one of the samples. So there's the data. So the first, I should back up a minute. The question was, what are you going to identify as the point estimator? Well, if they want me to estimate mu, the population mean, then a good point estimation or point estimator would be the sample mean, which we call x bar, remember. And that's going to be a point estimator for the population mean mu. So to find the sample mean is how I always find the sample mean. Add them up and divide by 50 in this case, and it comes out to 16.178 hours. Don't forget your labels. So then the second question, same problem. What proportion, call it P, of US, oh, I lied, not the same problem. Why are batteries up there? It's so confusing. What proportion P of US adults would classify themselves as vegan or vegetarian? So a Pew Research Center, I don't know if that's a real thing, a report surveyed 1,473 randomly selected US adults, and out of those, 124 said that they were vegan or vegetarian. So that was their sample. So the point estimator that they're using is the sample proportion, which remember we call p hat. And it's simply just a proportion. So the 124 out of the 1473, which measures out to a 0.084, and that is the point estimator, p hat, that we're estimating the sample proportion p. And then a third example, back to those batteries, that's why they kept them. The quality control inspector in Part A wants to investigate the variability in battery lifetimes by estimating the population standard deviation. So how would we estimate the population standard deviation, sigma? Well, we would use S sub x, the sample standard deviation, as a point estimator. So that was a sample standard deviation. I don't want to go through the math because remember, we hardly ever hand calculate standard deviation. We usually use our list one and then one variable stats. But it comes out to 0.664 hours is the sample standard deviation, which we are using as a point estimator for the population standard deviation. All right, that's a lot of vocab I threw at you. Guess what? There's more. So now let's talk about the confidence interval. So when the estimate of a parameter is reported as an interval, it's often called an interval estimate, or we call them confidence intervals in stats. And if you're taking an AP Bio course or you have, they use a lot of these, and for the life of me, the term is escaping me. They don't call them confidence intervals. I'm gonna have to look up what they do call them, but it's the same idea. So a confidence, oh, bar, something with a bar. Bar intervals, maybe? I forget. A confidence interval gives an interval of plausible values for a parameter based on the sample data. Plausible does not mean the same thing as possible, okay? Plausible just means that we shouldn't be surprised if any one of the values in the intervals is equal to the actual parameter. So we're going to see the language in a moment, but we just give a good estimate for where we think the true mean lies. And how good of an estimate is depending on the statistics we're willing to work with. So confidence intervals are constructed so that we know how much confidence we should have in that interval. See, this is such a math thing. Like, name it exactly what it is. The most common confidence level is 95%. That's also the accepted level that in your AP Bio class they tend to use, which we'll see in a moment is 2 standard deviations from the mean. I'll get back to that in a moment. So confidence level, they call it capital C, gives the overall success rate of the method used to calculate the confidence interval. That is, in C% of all possible samples that we could take, the interval computed from the sample data will capture the true parameter value. Okay, that's really vague because there's no context there. Let's see some context here. We're going to learn in a moment how to interpret the confidence level. So here is a formula, kind of a template for how you answer the interpreting a confidence interval question. So to interpret a C% confidence interval for an unknown parameter, you say, and I quote, we are blank % confident that the interval from blank to blank captures the, and then whatever you're trying to capture. So the mean of all test scores in Illinois, or the standard deviation of, I can't think of anything but test scores right now. I don't know why. And batteries, apparently. All right, note that some people include the phrase based on the sample data, and usually they'll kick off their statement with that, which I think is a good way to interpret, because remember, we're basing these confidence intervals off of sample statistics. When interpreting a confidence interval, make sure that you are describing the parameter and not the statistic. So over here, when they say captures the, and then this part has to be the parameter. So what you're trying to find about the true population, not the sample. I told you, they're real picky on language on these, so we got to watch it. To create an interval of plausible values for a parameter, we need two components. We need what's called a point estimate. We just talked about those, and we're going to use that as a midpoint. And then we need some sort of a margin of error. And I think we've all seen the margin of error concept in, they do this on election polling a lot. Well, they'll give a survey of some sort where they'll say, like, we're, thinking that this is the result. And then in the bottom right corner of your TV screen, it'll say, margin of error plus or minus 4.2%. And that's the margin of error that they're referring to here. And that accounts for all of our sampling variability, because we know from our work in chapter 4 that samples are not perfect. There's always variability in the randomness, and maybe we didn't really truly capture the true population's idea of what's going on, and we have to account for that. So here's the idea. We're going to have that point estimate, whatever we're using as a point estimate, and then we're going to have a plus or minus situation where we go to the left and right of the point estimate at a certain value. And that's going to have our C% confidence interval. Now, that's a lot of vague stuff. Let's get to some specific ideas. Here's an example of, there's no context here, but 0.65 is the point estimate. I have absolutely no idea what it is. Okay, well, that's all right. Apparently, P is the proportion of all U.S. adults who admit to experiencing some financial difficulty. Good to know. All right, so they found now remember, this is the sample data. So the point estimate they're using is P hat. So their sample proportion came out to 0.65 from whoever they surveyed or sampled. But then they're calculating a margin of error of 0.037, which is 3.7%. So they went up 0.037 and they went down 0.037. And this interval, which stretches from 0.613 to 0.687, is our confidence interval. So what we're going to say here in a moment is that we are 95% confident that the true population proportion of all U.S. adults who would admit to experiencing some financial difficulty lie between 61.3% and 68.7%. I hope I didn't just jump the gun on that one. Oh well. The margin of error of an estimate describes how far, at most, we expect the estimates to vary from the true population value. That is, in a C% confidence interval, so in this case a 95% confidence interval, the distance between the point estimate and the true parameter value will be less than the margin of error in C% of all samples. So in this example, if I took many samples from my population and I did all the sample calculations, 95% of them would contain the true what are we looking at again? The true population proportion of U.S. adults. That's pretty good. All right. Pardon my Starbucks chug. My throat's getting dry. Shout out to Starbucks. They make a mean chai. All right, 2 weeks before a presidential election, a polling organization asked a random sample of registered voters the following question. If the presidential election were held today, who would you vote for, candidate A or candidate B? And based on this poll, the 95% confidence interval for the population proportion who favored candidate A is from 0.48 to 0.54. So we're supposed to interpret that confidence interval. So what we say, and this is a quote, we are 95% confident that the interval from 0.48 to 0.54 captures the true proportion of all registered voters who would favor candidate A in the election. So according to our data, 95% confident that anywhere from 48% to 54% of people would vote for candidate A. Now, that's not really groundbreaking data. Let's talk about that. Part B here says, what is the point estimate that was used to create that interval? Well, if they were looking, remember what they wanted was the population proportion. So they had to find a point estimate at some point. Sorry to be redundant there. So what we can do is we can just find the midpoint of our interval, because that would represent the point estimate, which remember would have been p hat when they were sampling. So they must have used a p hat of 0.51. And then the margin of error, you can find a couple of ways. You can say, okay, 0.51, how far away is it from either of the endpoints? And it's 0.03 away. The other option is you can take the range of that interval and just cut it in half. That would be another way of figuring out what the margin of error is. So we're kind of working backwards. So based on this poll, a political reporter claims that the majority of registered voters favored candidate A. Now, by definition, a majority is over 50%. But remember, this interval stretched anywhere from 48% to 54%. So there's some significant values there that are under 50%, which wouldn't necessarily give that candidate a majority. So that was a bad interpretation of the poll by that pundit. The interval does not give convincing evidence that they've received a majority. It's a heated race, is what I would say. Literal tie. No, not literal, figurative tie. Interpreting a confidence interval. Here we go. As promised, we're going to show you what to do. So to interpret a confidence level, say if we were to select many random samples from the population and construct a blank percent confidence interval using each sample, about blank percent of the intervals would capture the actual and then whatever you're looking for. Again, this was a template for what we're going to say. Let's see this in action. So back to this question. Blah, 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 interpret the confidence level. So we say, if we were to select many random samples of the same size from the population of registered voters and construct a 95% confidence interval using each sample, about 95% of the intervals would capture the true proportion of all registered voters who voted in favor of candidate A. All right. Well, I shouldn't say voted. It didn't happen yet, but you got it. So that's kind of like a really wordy thing to be able to say. But the idea is when I say we are 95% confident that, and then this is a different statement, but it's really coming from the same place, I should say. So if we were to sample many, many random samples from the population and construct a 95% confidence interval using each sample, 95% of those intervals would capture the true proportion of voters who are going to favor candidate A. This is a good visual for it. So you have, this is a little hard to read here, but the population distribution is here in this purpley color, and the sample distribution is this red dashed line. So a sampling distribution, remember, is just made up of a whole bunch of samples. And they've kind of captured the intervals down here on this axis. And you'll notice the true mean, which for the previous example, it would have been p hat, but you got the idea. Or p, excuse me, not p hat. But in this case, the true mean is this green line, the middle of the population distribution. So you'll notice each of these intervals, even though it's not necessarily centered on it, it does hit this green number in almost all of them, and the only exception is this red one. So we can do some simulations where we can see where this is true. So 95% confidence means that if you had 100 samples that you took, 95 of them would actually hit that green line and 5 of them wouldn't. I think we'll do that as an activity later. That sounds fun. Oops, I should have brought this up. Once a particular confidence interval is calculated, its endpoints are fixed, and because of the value of the parameter is also constant, a particular confidence interval either includes the parameter or does not. So the ones that included the parameter are black, and the one that didn't was red. confidence level does not tell us probability that a particular confidence interval captures the population parameter. That's a common misconception. Anytime we see a percent, our brain likes to think of probability, but that's not what it's measuring. Exam tip. We'll take all the tips we can get. Go ahead, guys. It's coming up soon. On a given problem, you may be asked to interpret the confidence interval, the confidence level, or both. So be sure you understand the difference. The confidence interval gives a set of plausible values for the parameter. So it's like they say we're 95% confident that the parameter lies between here and here. And then the confidence level describes the overall capture rate of the method. So many samples, 95% of them would have captured the true mean. I know it feels like they're saying the same thing, but they are saying different things. So we got to be careful with the vocab, like always. All right, so here we have an example. The Pew Research Center. I guess it's a thing. We should look it up. Smithsonian Magazine recently quizzed a random sample of 1,006 adults on their knowledge of science. One of the questions asked, which gas makes up most of the Earth's atmosphere? Do you think it's hydrogen, nitrogen, carbon dioxide, or oxygen? I don't think I know the answer. Huh. All right, a 95% confidence interval for the proportion who would correctly, nitrogen. The right answer is nitrogen. Who would correctly answer nitrogen is anywhere from 0.175 to 0.225. I don't think I would have been in that interval, guys. So 17.5% to 22.5% is they're saying they're 95% confidence interval. So your first task is interpret the confidence interval, then interpret the confidence level. Remember, two different things. Calculate the point estimate and the margin of error. So kind of working backwards from your interval. And then if people guess one of the four choices at random, about 25% should get the answer correct. Does this interval provide convincing evidence that less than 25% of all US adults would answer this question correctly, and explain your reasoning? All right, so pause the video and think about those questions and jot down your thoughts. Here comes the answers. All right, so for our confidence interval interpretation, we say we are 95% confident that the interval from 0.175 to 0.225 captures the true proportion of all US adults who would answer this question correctly. And then the confidence level. This is the one that kids are a little leery of because they're not really sure if they're answering it right. So if we were to select many random samples of the same size from a population of US adults and construct a 95% confidence interval using each sample, about 95% of the intervals would capture the true proportion of US adults who would answer the question correctly. All right, so now working backwards from the interval, to find the midpoint, you add up the endpoints and divide by 2. So the point estimate must have been 0.2. Remember, they were trying to capture the proportion, so this would be a p hat. And then the margin of error, we'll talk more about how that comes up later, would have been, the distance from the middle to the edge. That's one way to find it. So that was a distance of 0.025. And then the final question about the 25% thing. So remember, it's like a 1 in 4 chance of being right. So they're wondering, like a 25% chance of getting it right, does this kind of correlate with what you're seeing with this interval? Of all the plausible values in the 95% confidence interval, they're all less than the proportion expected if people were just to simply guess from the 4 choices at random. Therefore, this interval does not provide convincing evidence that less than 25% of all US adults would answer this question correctly. I'm sorry, I read that totally wrong. I was like reading it and I was like, that doesn't make sense. This interval does provide convincing evidence that less than 25% of all US adults would answer correctly. So look, the interval didn't even hit 25%. And you got to remember, like when you say, I have a 1 in 4 chance of guessing the right answer, that's like a sheer blind guess probability question, guys. You do have a little bit of knowledge about the atmosphere. People come into that question with some knowledge. So they have something working in the background that might guide them to one answer or the other. So it's not as simple as a 1 in 4 chance anymore. So there's the data. It doesn't provide evidence. No, it does provide evidence. Why can I not read today? The interval does provide evidence, convincing evidence that less than 25% of US adults would answer this question correctly. I'm going to be quiet now. No. So I have a feeling that's probably where we stop day 1 and hope I make less mistakes when I actually teach it. A girl can dream. All right, so let's talk about, well, margin of error. That doesn't sound like a good thing to have. Like, you don't want a large margin of error because that means your statistics are kind of weird. And people don't really want to hear that. Like, oh, the answer is zero point 0.5 plus or minus 35%. Like, no, that's too big. So we want to get margin of error as small as possible. So here's what we can do to decrease the margin of error. Well, you can decrease your confidence level. So if you don't really care about being 95% confident, maybe you'd be okay with being 80% confident. Maybe not. So if you're not okay with decreasing the confidence level, because as you can see in this visual, the confidence level, when you shrink it, will shrink the interval, meaning you have a lesser margin of error. The other thing you can do is increase the sample size. So in general, anytime you increase the sample size, it's going to reduce the margin of error for a fixed confidence interval. So if you want to keep that 95% confidence interval and you're not happy with the margin of error that's being produced, then you're going to have to increase your sample size. And we know that when we do that, we're going to see something more true to the value of the population's proportion or mean or whatever we're looking for. So this is an example, and I've seen these on the multiple choice test before where we got to think about the algebra here. If they were to quadruple the sample size, think about putting a 4 here, that's going to end up cutting the margin of error in half. Okay, so this is mathematically, it's part of the formula for finding margin of error, but we'll get to that later. The margin of error does not account for any sources of bias in the data collection process. Guys, there's a reason we started with that chapter. Data collection has to be unbiased. Otherwise, everything you do after that is going to be thrown out as garbage. So margin of error is assuming that everything went to plan and you sampled properly and you didn't ask weird questions on your survey and you didn't have, like non-response bias, you didn't have all that good stuff. So we got to start connecting those old ideas as we get closer to the AP test. There's some questions, especially in the free response, that where they kind of pull on your knowledge from various chapters. So that's what makes this test so fun. All right, so for a normal sampling distribution, extending about 2 standard deviations in each direction produces the approximate 95% confidence interval. And that's the typical one that most people are happy with, especially in AP Bio. You'll see the 2 standard deviations is what they want. If you go 3 deviations out, though, you are 99.7% confident. So that's better. The more general formula for a confidence interval is the statistic plus and minus a critical value times the standard deviation statistic. Sorry. So you might be wondering, what's this critical value they speak of? That will come later. It's a multiplier that makes the interval wide enough to have the stated capture rate. It's actually on the chart. You'll be surprised. We're going to have some things really come together here in this chapter 8. The chart I'm referring to is a chart that is, well, I don't want to give too much away. Okay, I want to say it yet. Never mind. Okay, what affects the margin of error? As a part of a project about response bias, Ellery surveyed a random sample of 25 students from her school. One of the questions in the survey required students to state their GPA aloud. Based on their responses, Ellery said she was 90% confident that the interval from 0.4 to 0.72 captures the proportion of all students with at her school, with GPAs greater than 3.0. Explain what would happen to the length of the interval if the confidence level were increased to 99%. So if she now increases her confidence level, she is going to widen her her interval, because that confidence level increase is going to give her a bigger margin of error. So how would the width of a 90% confidence interval based on the sample size of 100 compare to a 90% confidence interval assuming the sample proportion remain the same? Well, so remember that weird little cute thing where we had like 1 over square root of n? Well, look, she quadrupled her sample size. So the confidence interval would be half as wide because of that formula. I wish they put the math here, but like if it's a times 4 factor, 1 over the square root of 4 is half 1 over 2. Okay. So describe one potential source of bias in Ellery's study that is not accounted for by the margin of error. Well, girl, you asked them to verbally say what their GPA was without any sort of like anonymous like answering method. So I don't know that people were truthful is the issue. The proportion of students with GPAs greater than 3.0 might be even less than the point 0.4 that she calculated. So her interval here is, in my not very professional opinion, probably not capturing the true proportion. Sorry, Ellery. Now, if her purpose of this was she then did a different sampling method where she didn't have them write them out loud, say them out loud rather than write them down, maybe she'd see something different. I don't know. That's for Ellery to figure out. Sounds like a good final project, doesn't it? All right, guys, that was the end. You know what? I lied. When I said it was going to stop at a margin of error, making it larger or not, I don't know that that's true. Oh, well. Wouldn't be the first time I lied to you on the internet. All right, guys, good luck, everybody. Whoops. Guys, I can't get out of my video.